Welcome PCS members and our friends to another PCS IBS seminar. It is a great pleasure to have with us today Kévin Hémery from TUM Munich. And I would like to invite our scientific host, Dario, to introduce our speaker. Please, Dario.
Okay, thanks, Dylan. Yeah, it's a great pleasure to have Kévin today here for our talk. So let me introduce him. Kévin is a very young scientist. He's a PhD student right now in the group of Professor Frank Pohlmann in Munich. And despite his young age, he has already a couple of papers which are very interesting and related to computational methods in quantum many-body physics, in a broad sense. And his subject of his thesis that he's developing is efficient tensor network simulations of localized and ergodic systems. And related to this subject today, he's going to talk about identifying correlation clusters in many-body localized systems. So Hémery, please, Kévin, you can start.
Well, thank you, Dario, for the kind introduction and for the invitation. It's a great pleasure to be here to be able to talk about this work. Right. Okay, so let me just say a few words about the content of my talk. So in the first part of my talk, I would like to take some time to talk about thermalization and many-body localization. So if you feel completely comfortable with the concept of many-body localization, please feel free to tell me that I should move on. So I thought it was a good idea to spend a bit more time on the introduction to be clear about the concepts of many-body localization. Otherwise, it would not make sense to present my results. But if it's too long, please just tell me. Okay, and then in the second part of my talk, of course, I will talk more about the work, which is about identifying correlation clusters in many-body localized systems. Okay, so first, let me just present a bit my collaborators. So we are working at this TUM, Technical University of Munich, in the south of Germany in Bavaria, not too far from the mountains. It's very nice. So we did this work in collaboration with Adam Smith, who was a postdoc in our group, and of course with my supervisor, Frank Pohlmann. So let's start with thermalization and try to understand a bit better what we mean by thermalization, especially for quantum system. So first, it's good to start with a simple example of classical thermalization. And one key feature of thermalization for classical systems that we have a loss of information about the initial state. So if we take an example here of the glass of water with some ice, when we do the time evolution of the system, then the ice melts, right? And it's impossible to say at the end when we have this homogeneous system that we started from this inhomogeneous system with ice and water. Okay. So another question is, how can we generalize this idea of classical thermalization to quantum systems which are closed, right, which are isolated? And one remark I would like to make at this point is that in this talk we are going to talk about isolated system. And of course, this is an approximation, right, because you could argue that any system is always in contact with the environment, but in many cases it turns out it's a good approximation to consider insulated system, right? In this sense, you can describe this glass of water as being isolated of its environment, although it's not true, right? And recently there have been a lot of progress and experiments to realize better and better isolated systems. So that's why it makes sense, right? And so once we have understood what it means for isolated quantum system to thermalize, I will try to convince you that thermalization is not completely universal, and actually we can find exceptions to thermalization. Okay, so there are kind of two questions or paradoxes when we talk about quantum thermalization. The first thing is, for an isolated system, we know that time evolution is unitary. And this is a bit of a problem, right? Because you cannot imagine having a loss of information with a unitary time evolution. And the way to resolve this paradox is if you take a system prepared in an initial state and then you do the time evolution, there is a loss of information about the local information, right? So if you, after the time evolution, if you do just local measurement on the state, you cannot, if the system is thermalizing, you cannot tell what was the initial state locally. So that's the way to resolve this first paradox. And now the second paradox is, in principle, everything is contained in this Schrödinger equation. So it seems that just from quantum mechanics, you could deduce statistical physics, and it's not easy to see why. All right, so you can just take the Schrödinger equation, or rather the Heisenberg equation, you do your time evolution, and this should correspond to the macrocanonical ensemble, and it's not at all obvious why. Okay, and so to resolve this second question, or this second paradox, it can be helpful to have again this picture, here this cartoon picture, and saying that you have one subsystem embedded in a much larger system, and you can take the left and the right of the system and say that it's a bath which is going to thermalize the central system. Okay, but so this is an intuitive picture, but so what is often said about this is that the system acts as its own bath. And there is a way to make a more rigorous, to have a more rigorous understanding of this statement. And this is with what is called the Eigenstate thermalization hypothesis, ETH, which is fairly recent, considering that it's a natural question to ask how from quantum mechanics we can derive, in some sense, statistical physics. Okay, and the way to answer this question is that the eigenstates themselves are thermal states, in the sense that if you take the expectation value of an operator with respect to an eigenstate, then you will have the same result as if you would average this operator over a statistical ensemble. And so keeping this in mind, when you do time evolution, in the long time limit, essentially what you're doing is simply averaging over eigenstates. So of course there are off-diagonal terms, but due to dephasing, this will decay eventually, right? And we are left with just this average over initial state, right? And over eigenstate. Ci here is the initial overlap with the initial state of the initial state with the eigenstate I. Right, and so that resolves the paradox, essentially that this idea that the eigenstate are thermal. So there is a question.
Yes, we have a question. Alexei, please.
Yeah, sorry, I have a very simple question. So I guess an implicit assumption is that you don't have long-range correlations in your system, like, or say if you have a long-range hopping or perhaps even long-range interaction, I guess things might break down in some sense here.
Right. So the main assumption here, so why ETH explains this thermalization is because you have an initial state which is peaked in energy. So that's the assumption that you need. And indeed, if you think about the local system, most of the states which have short range correlation will have these properties that it's peaked in energy, right? So only a small region of the eigenstates overlap significantly with your initial state. Right? Yeah.
Yes, so that's exactly what I'm asking. So I presume that if your Hamiltonian is long ranged, then there might be significant deviations.
No, but so it all depends on your initial state. But in general, if you start from an initial state, let's say, which is sampled from a statistical ensemble, then you will always have something which is peaked in energy, even for a long-range system.
Okay.
Yeah. Thanks for your question. Okay. So now, if we go back to this idea of eigenstates being thermal, what we would like to see is that the expectation value of this eigenstate will smoothly depend on the energy, right? Because we want just this eigenstates to reproduce properties of statistical ensemble, and smoothly depending on energy is exactly what an ensemble would do. And so there have been like very large calculations done with this respect. You can see here from this paper from Marcos Rigo. And so here we measure, so they measured like an operator, which is just the occupation number of a given momentum as a function of energy. And you see that this agrees very well with the prediction of ETH. So although it's just an hypothesis, we have really a large body of evidence numerically that this mechanism is really what is happening during thermalization. Okay, but so you see that actually thermalization that we thought as something completely general, stems from a very specific mechanism. And that's why it's a logical question to ask whether we can find robust exceptions to this process. So of course, you can think about fine-tuned models such as integrable models, which will not satisfy ETH. But let's see if we can find something more. Okay, so right. So a good place to look is to start from some non-interacting systems that we understand very well. And so, of course, there is this Anderson insulator, right? So let me remind briefly what it is. So if you look at a single particle in a periodic potential, we know that the solution are Bloch wave function, which are extended through the system. But now, as soon as you start in 1D to add some disorder in your potential, you find that the wave function of the system become localized and exponentially localized. Okay, so that's a very interesting. It's a very interesting phenomenon, and the question is, can we make this a bit more universal in the sense that can we add interaction and have this localization property still holding? Okay, so let's add interaction to this Anderson model. And what happens is that if you start to add interactions, the localization of the wave function still holds for the many-body case. Okay, but if you add too much interaction, then you have a phase transition, and then you go back to a thermal phase, right? To a phase which satisfies ETH. And so on the same way, you can think about first adding some interaction and then add some disorder to your system. And then if you add enough disorder, we'll have a phase transition for from something which is thermal to something which is localized. Okay, but so it's a very peculiar type of phase transition. It's called the Eigenstates phase transition because all the eigenstates fill this transition. Not necessarily at the same point as the phase diagram, but for all energy density, you have a phase transition. And so this is what he's demonstrating here from this figure taken from this paper of David Lewitz and collaborator. So here it is epsilon on the y-axis is the energy density, and h here is the disorder strength. Okay, and you see that at every energy density, there is a critical disorder where you see this phase transition between these two phases. Okay, so it's also called a dynamical phase transition because simply dynamics is entirely understood from the eigenstates, right? So once you have the eigenstate, you can deduce what the dynamics will be. Okay, so and this is very counterintuitive because if you think about the classical counterpart of this, you would take a glass of water, you would put some ice in it, and then the ice will never melt. So that's very surprising. And so to convince you that it's really a thing, let me show you some experimental results. Okay. So to identify this very special phase of matter in experiments, what people do typically is to look at an observable and to know where you know in advance what the thermal value should be, and then to observe that in an MBL regime, you do not relax toward this expected value. So a nice way to do this is to start from an initial state, which does not have an homogeneous density, right? So only the odd sites are populated and you leave the even sites empty. And now when you do the time evolution, if you are in the ergodic regime, you obtain a uniform density. At the opposite, if you are in the MBL regime, you have an uneven density, and you have peak of density on the odd sides and low density on the even side. And this is because the system keeps the local information about the initial state, right, which is completely non-thermal behavior. And so, and this is measured. Yes, please. I see there is a question.
Yes, I have two questions actually.
Okay.
Yeah, one is how do you make sure that you didn't wait long enough? I mean, maybe if you waited longer,
right. So that's already
it would reach the equilibrium.
Right. So yeah. So that's a question that whether this is really like the long time limit or whether this is just a like pre-thermalization behavior. Yeah. So I don't think in an experiment you can really. So the only thing you can say is like do it theoretically and see that you can time evolve as long as you want, and the behavior is.
Yeah, but aren't there some time scales that when you reach them, you are supposed to be fully thermalized? So maybe if you don't reach it by that time.
Right, but it's hard because it's very hard to predict. I give you a thermal system, then it's hard to give a time where to predict the time where it's going to thermalize. Right, so in principle, there are systems which takes very, very, very long time to thermalize.
You see, and the second question, because you said this MBL is very non-classical, but quite clearly that there are crystal structures that are exactly like this, right? You have one molecule, a different molecule, one molecule, different molecule. Even not spaces are just different molecules. Well, not molecules, atoms in crystal structure. I just wonder, what's the meaning of this statement? It's not classical, or it's not thermalizing.
So the meaning of the statement is exactly that if you take, an operator, and then you wait like until an infinite time, then you will never relax this toward what is predicted by statistical physics. You will never reach the macrocanonical ensemble.
Well, but that's possible also in classical physics, right? I mean, you have non-integrable systems.
Right, but so of course there are non-integrable systems, right? But this is just a fine-tuned example, right? You have one point in the phase diagram when this is non-integrable, and then when you start to perturb it, then you move away from this non-integrability. Okay, and here it's different because it's a Wolf phase of matter where you just simply don't reach thermal value, right? So you can add the perturbation, you want more disorder, more interaction, then it's stable against this perturbation. So in this sense, there is a difference with integrability. Okay. Right, then also,
okay.
For integrability, there's this generalized Gibbs ensemble and so on. So it's so there is some kind of.
Yeah, I still don't understand why is it so special, but I guess maybe for this further discussion afterwards.
Okay.
Thank you.
You're welcome. And I see another question here.
Yes, I want to clarify. So you said that you wait for infinite time and the system doesn't thermalize. Do you mean this for thermodynamical limits of an infinite system? Right.
So actually there is a debate right now, which is very interesting, of whether this claim holds for infinite for thermodynamic limits, and actually there is not really a proof of that. So there are people who say that this is just finite size effect, and then when you will go to the thermodynamic limit, you will end up thermalizing. Okay, so it's a debate, but people think that this result that we have for finite size systems, they also hold in the thermodynamic limit if the disorder strength is sufficient.
But that's not exactly what I mean. I think I thought that it's known that for not infinite systems or finite systems, still MBL phase will thermalize. It just takes times that are exponential in the size of the system.
No. So that's the point, that MBL phase will never thermalize. So that's what's special. So there are other systems, where it takes a very long time to thermalize, or for example, there is pre-thermalization, or there are other kind of exceptions where some states take very long time to thermalize, but this is never the case for MBL.
Okay, then for example, we know that entanglement entropy does grow, though only logarithmically in MBL phase. Right. So, which indicate that at some point a transition should happen, some transition. So then which of this transition is, if not thermalization?
Right. So the point, there is never thermalization. So maybe I can come back to this question because I will talk about the growth of entanglement a bit later. Okay. So maybe let me try to answer this question.
Thank you.
Okay. Right. So yeah, to go back to this experimental results, right, there is this quantity which is called the imbalance, and this is the difference between the population of odd and even sites, right? And for the MBL regime, what you see is that this operator will oscillate, at a value which is not thermal. So the value which is thermal would be 0, with delta being the disorder here. When it's 0, you reach thermal value, and then when you put some disorder, you see non-thermal behavior. Okay. And now in 2D, there is even like a more intuitive result where you put all the particles at the left of your system, and then you let the system evolve. And for the ergodic case, then the full system is populated. And in the MBL regime, you see that only the left side is fully populated. Okay, so these are experimental realization of non-thermal behavior. Okay, so now we have seen like this first difference between ergodic and MBL. Now let's look about the eigenstate. Let's look at the static properties to understand better the difference. So when you would look at the entanglement of the eigenstates of a generic ergodic system, you expect to have volume law. And in practice, what volume law means is that every site is entangled with every other site. Okay, and in particular, if you take the bipartite entanglement with a cut, the entanglement will strongly depend where you take the cut, right? So to understand this, you can imagine taking measuring the entanglement between the left part and the right part of the system with a cut between the first and the second site, right? And you're just measuring the entanglement between the first site and the rest of the system. But now if you measure in the middle, right, you have much more sites interacting between each other. You have all the left side and the right side of the system. And this is illustrated here. So this numerical calculation, right? And for low disorder, this deep blue curve here, you see that as functions of the length of the cut, entanglement grows linearly. So this is characteristic of volume law. It depends on the volume of the cut. On the other hand, for many body localized system, you have area law. And what area law means is only sites which are nearby from each other interact. And if you take a cut, no, there are only the sites which are really close to this cut which will contribute to the entanglement. And what this means is if you move the cut through the system, you will have constant entanglement through your system. And this, for high disorder, you will get the orange curve. Okay, where you see the entanglement, except for the boundaries, in the bulk of the system, entanglement is constant as a function of the length of the cut. Okay, so another difference is like high entanglement of the eigenstate vs small entanglement of the eigenstate. And
sorry,
there is,
Kévin,
yes,
I have a question about that. Can you go back?
Yes.
Yeah, I mean, in this intermediate regime, do you see effects? I mean, do you see effects of the mobility edge or not? Like if you do, because, you know, at the intermediate regime of the disorder, you have the mobility edge. So maybe depending on which particular eigenstate you take, you can have different results or
yes. Yeah, so of course, if you take ground state, right? Sorry, yeah.
Sorry. Go.
So if you have ground state, if you have a gap system, of course you will always have area law, right? And so of course, like the lowest lying eigenstate will be less entangled, right? But here we're talking, so I should have been more precise. We're really talking about the highly excited states, right? So typically in the middle,
so you are in the center,
right? And of course, when you go down in energy, into low energy sectors, then you will have, even for ergodic system, area law, right? At some point.
Okay.
So indeed, there is this dependence of the entanglement of the eigenstate, depending on where you are in the spectrum. Thank you. Okay. So now let's look at the dynamical properties, right? So so there is something equivalent with the entanglement. So for the ergodic case, let's say you start from a product state, then you do a quench, you get something which is a linear growth of entanglement as a function of time. And now, when we talk about MBL, you have something which is logarithmic as a function of time, right? And here, here's this blue curve is for the case where you don't have interaction. So it's Anderson insulator, and you see that here, after some time, entanglement doesn't grow anymore, right? So this is a marker of the difference between interacting case and non-interacting case. Right? And so also this has consequence, maybe to try to answer the question which was asked earlier. So if you take a system of a given length, right, you do the time evolution, right? So the entanglement of the system, once all the information have propagated to the edge of the system, for the ergodic case, you will reach the page value, right, which is the maximal entanglement you can have in 1D. And MBL, you will reach also a value, but it will never be this page value. It'll be much lower entanglement. Right? So this is the difference between the two phases in terms of entanglement. Right, and that's why, yes.
Yeah. Okay. Thank you. But then, could you clarify? So, okay, this value to which it will saturate. So it is still the same phase. So you say that logarithmic growth that we see, it's only an artifact of initial conditions.
No. So what I'm saying is just like, so typically you want to look at a quench, but at the beginning you don't have, you have an initial state with no entanglement, which has overlap with all the excited states, if you want. And then you do the time evolution, and then you have this logarithmic growth of entanglement. Of course, if you start from a fully entangled state, right, I mean, you will observe something different. So you need to start from something which has no entanglement to observe this logarithmic growth. Okay, so of course you can find special states where you don't observe this, but this is not like the general quench protocol, where you have the right overlap with all the states in the middle of the spectrum.
Okay, thank you.
Thanks. Okay, right, so let's move on. Okay, so now we have seen different properties, and actually there is a unifying framework to understand these differences between the two phases. And this is a theory of local integral of motions. And so the idea is that actually there is a kind of emerging integrability in this system. More precisely, there are emerging local quantities due to the disorder, but these conserved quantities are very special because they are quasi-local. So here, so these quantities are called the tau Z matrices, and if you look at this operator, it's actually exponentially decaying in real space. Okay, so this is a very special conserved quantity, right? So when you diagonalize the Hamiltonian, you do this unitary transformation, and this unitary transformation is quasi-local. And now when you express the eigenstates, you can express them as product states in this tau Z basis. So this first explains why you have lowly entangled eigenstates in your system. Okay, but also in your Hamiltonian, if you do this construction, you will see that there is an exponentially decaying interaction between this tau Z matrix, and this is responsible for this logarithmic growth of entanglement. Okay, so now we have like a good theory to describe what is happening deep inside the MBL phase transition, and this is quite well understood. But now what is not so well understood yet is what exactly is happening in the transition. So what is the process which leads to this delocalization transition? What is the scaling and so on? And that's where we started. That's why we did this project. And now I'm going to start the second part of my talk where we focus more on our results. Okay, so just as a motivation, what prompted us to start this project is that recently there have emerged promising phenological approaches to this phase transition between MBL and ergodic. And so there have been renormalization group approaches to try to understand what happens. And so here I'm trying to give like a toy picture of what people are doing in these RG approaches. So they are postulating that even in the MBL phase, there is a coexistence of regions of space which are localized, right, which they call insulating block. But there are also maybe rare regions, at least deep in the MBL phase, which locally look thermal, and they are called thermal block. And now they define rules to update this state and to move to a different step with the idea of explaining the phase transition. Okay, and so one simple rule here that I've explained is like, that I've tried to illustrate here is if there are two thermal blocks surrounding an insulating block, and if the thermal block is bigger than the insulating block, then it can thermalize the insulating block in the middle, right? And it's a process, this process of thermal block invading insulating block is something referred in the literature as quantum avalanche or avalanche instability. Right, and so at the next RG step, then this insulating block will be merged into these two thermal blocks, and then you have one bigger thermal block. And then if you continue to do this RG step, you will cross the phase transition and arrive in the thermal regime where you have only one big thermal block. Okay, so this is just phenomenological. It's not based on microscopics, so they are just hypotheses of how things are happening. And the goal of our, or at least the initial motivation of our work, was to try to bridge these phenomenological approaches with the microscopic models. Okay, and so as I've said, like these approaches rest on some hypotheses. Okay, and so for example, we don't really know a priori the structure of the eigenstates. So what I've presented at the slide before, we had local clusters, right? So we had like some maybe ergodic, maybe some insulating blocks, but they were all local, right? But this is just an assumption put by hand at the beginning of the RG, right? And so you could also imagine having a state which is more like an ergodic skeleton with longer range interactions, and then when you decrease the disorder, then the insulating blocks in the middle of the skeleton would merge with the skeleton, right? So this we don't know, and then we need really to look at the microscopic to know precisely what is going on. Okay. So now to do this, first we study what can be called the Drosophila of MBL, right? Which is the XXZ disordered model, which is just a standard spin chain, right? With a hopping term. If you do Jordan-Wigner, then you get fermions hopping from side to side. Then you have the interaction terms with this delta factor in front. And if I take delta equals 0, I go back to the Anderson insulator. And then, of course, there is a disorder term, right? Disorder which is introduced with this random variable which is sampled uniformly between -W and W. Okay, and now we would like to have the states of this Hamiltonian and then try to identify the block structure of the states. But there are several challenges to do this. The first thing is, if you don't put any assumption at the beginning, there is an exponential number of possible partitions, right? And so we cannot evaluate all of these partitions. Right? And the second challenge is what the quantity which you would like to have in order to determine this clustering of your system is the entanglement, and it's very hard to obtain, let's say, the multipartite entanglement of your system. First, theoretically or numerically, but even in experiments, it's even harder, right? You would need to do the full tomography of your state. So it's very difficult. Okay, so we need to try to overcome these two problems. Okay, and there are two ingredients that we have used to do this. First is not to look at the entanglement, but to look at the correlations, which are easily accessible in numerics, but also they are accessible in experiments. So it's a nice place to start with. And then to solve this problem of exponential number of partitions, we use tools borrowed from graph theory, which are highly efficient. And as you will see, this solves also the second problem. Right? So the starting point is to construct a graph. And of course, like the nodes of our graph are the sites, right? And then the edges of the graph are just weighted according to the correlations, right? So this is just saying that what is called the agency matrix is just the correlation matrix, right? So you can take, for example, the two-side mutual information, which is quantity which contains all the correlations of your system. You can simply take correlations function, for example, especially if you are interested in experiments. Okay, and now there are two ingredients for the graph theory algorithm. The first ingredient is we define correlation clusters. Okay, and so the idea is that like two sites belong to the same cluster if they are strongly correlated, and on the other hand, if two sites, so like if two parts of the system do not share any strong correlation, then they are very likely to be in two different clusters. Okay, and we use this intuition to first find a hierarchy of the different partition of our system, right? So we start from our initial graph, and then we remove the weakest bonds or the weakest link between the sides, okay, until, and we do this recursively until we have splitted our graph in several parts, right? So here we remove like this two weak bond here, and we arrive at the second step at the first partitioning our system, or first clustering our system, right, where you have two different clusters, and we do this recursively, and then the next possible clustering contains 3 clusters and so on, and we can do this until we have completely separated sides in the end. Okay, so now we have a linear number of partitions, which is already better than exponential.
Sorry, Kevin, I'm getting lost a little bit, so can I ask a few things?
Yes.
I mean, I don't understand how you. I understand that the sides are the nodes, but the edges. I lost how you understand the edges to start with. So let's try to be, let's say, as simple as possible. You have a certain eigenstate, right?
Yeah. Mm-hmm.
Okay, and you have, let's say, the amplitude of each this eigenstate over each node. This definitely. No, wait. Yeah. Okay, go ahead.
So let's say you measure a correlation function between every side, right? So let's say sigma z correlations between every side. Okay, so between one and you measure zz and so on, and then you say this is the edge between sides 1 and 2. Okay.
I see.
Right. So you measure correlations between all pairs of sides, right? These two side correlations.
And the choice of the observable is arbitrary. Okay, now you said, let's say sigma z. Why sigma z?
Right. So actually, the most general choice you can take is this two-side mutual information. Okay, because this contains sigma z, sigma y, sigma z. It contains, like, for example, for a spin system, it contains 9 types of correlations, right? So it's a proper correlation measure, right? But so if you know more about this system, as we do, we know, which correlations will represent well our system, right? Which correlations will cause entanglement in our system. And for example, for this XXZ model, we can talk about this a bit later during the results, but we know that the Z correlations will be particularly important, right? Because that's where you have
and then you start to cancel, let's say, the weakest node, and you create several of these figures, right? I mean,
yeah.
But when this procedure stop, or how you decide what is the relevant?
So this I haven't explained yet. Okay, so this is
okay, good.
This is my second. This is my second ingredient, that we have to choose among these possible partitions, right? Which is the best one?
Okay, so before going there, I don't understand the quantity Q. The quantity.
Right. So that's exactly my second ingredient. So
okay, sorry. Okay,
right.
Please go.
So Q is a quality measure, and so it's something which is taken from graph theory, and it tells you how good the clustering of the system is. Okay, and it's a bit complicated, like, let's say, the mathematical formula, but essentially it compares your partition with the same partition done in a random graph, and it tells you how much better you are than in this random graph. Okay, and what I mean by a good partition is, like, inside a cluster you should have like strong correlations, and outside two separated clusters you should not have too much correlations, right? And so that's what his quality factor is measuring. In the technical term in graph theory, it's called modularity. Okay, and it's designed in such a way that, for example, the number of clusters do not influence this quality measure, right? So it's something which is rigorously constructed. And since we have this tool, with this partition that we have obtained, we can just cheaply measure the quality factor for every of these partitions, and then we just have to pick the one which has the highest modularity, the highest quality. And then we have found what is the best clustering of our state.
And somehow you say you don't have to worry about, let's say, this is a finite procedure. So in any case, you can generate all the possible, let's say, clusters, and then all the possible partitions, and then keep the best, right?
Exactly. And not only it's possible to do it, but it's very efficient to do it. It's very easy to remove bonds. Then I have very few. I just have some numbers to store, like which are the sites which are grouped together, what are the correlation between these sites, and then in a fraction of a microsecond, I can just evaluate on the computer what is this modularity. And so actually, it's like
Can I ask just a final question, and then I let you continue? I mean, let's say in the first step, you decided to cancel 2 edges. So I guess you put a cutoff such that you say, okay, below this cutoff I cut, or
so now it's even simpler than this, right? So you start, you look at all your edges and you take the minimum and then you remove it, right? And then you do this and the second one. And
so
here
you do one by one.
You do it one by one, and here I've just shown like the intermediate step where finally you have something splitted, right? Because when you remove one, for example, here let's say you would remove this one, then this site is still connected to the whole system, right? And it's only when you remove the second one that you find the first partition.
Okay, thanks.
Okay, thanks a lot for your question. I hope it helped to clarify the algorithm. Okay. Right. So now that we have explored in detail this algorithm, let me show you, jump a bit ahead and show you what this gives in practice. So here here I show a correlation matrix. I mean, more precisely, it's a two-side mutual information matrix, which capture all the correlations between pairs of sites. Okay, and I've applied my algorithm, and now I look at what are the clusters, right? So these are inside these red boxes, right? And the first thing to see is inside the box, you have strong correlation between sites, and outside the box, either you have like 0 correlations or you have very weak correlations. Okay, so that's the first. So our algorithm is working correctly, but also we can compare with the bipartite entanglement. And what we find is that in the frontier between 2 clusters, we always find a minimum of bipartite entanglement entropy, okay, which is very reassuring. So that's the second point. Now, the third point is that there are 2 types of clusters. There are these local clusters, right, which are inside these red boxes. And then we have also like delocalized clusters, which are in here, it's in green and in yellow, right? And so this is quite nice because actually the graph theory is not, we did not put any physical assumption into it, right? So for example, graph theory doesn't know anything about the position of the sites in the system. So it's not just toward finding local clusters. Okay, so we find some examples of these delocalized clusters, but now we can do this for many eigenstates and see what is a general picture. And what we find is overwhelmingly the majority of clusters are local. Okay, and we don't find any evidence of this ergodic skeletons in all the eigenstates that we have obtained. Okay, so this is the picture that we get. We have an idea of what is the structure of the eigenstate in terms of locality of the clusters. Okay.
And this is done in the deep in the MBL.
Right, so
regime,
this is
right?
deep in the MBL indeed, right? Because it's the more you go towards the other phase, the more difficult it is. Right, so let me say a word about this. So now I'm going to talk about the matrix product state approaches to MBL. So how do we, so you've seen here, it's a huge system, so right, it's 50 by 50. So right, it's a chain of 50 sites. So this is impossible to do exactly. So how is it that we can do this? And this is thanks to the power of MPS. So there are 2 main ingredients for this numerical methods. The first ingredient, in order for it to work well, you need to have area law. Okay, and this is perfect for MBL because we have seen that the eigenstates follow precisely area law. So this is very nice, and this is the reason why MPS works. Is actually where, so of course the Hilbert space is used, right, 2 to the power 50, and it's impossible to store on the computer, but there is this small corner of the Hilbert space where it's possible actually you have a good variational ansatz, right, which is MPS, which can represent any state within this small corner with arbitrary precision. Okay, and the second maybe more technical point is that once you have this ansatz, you can transform, like a global optimization problem of finding, let's say, the ground state, or in this case, an eigenstate with 2 to the power 50 numbers, which is very hard to optimize, right? Even if you could store it in the memory, to something which is local. Okay, and that's what you should get from this maybe a bit complicated figure here. So this is just a tensor, which is called the effective Hamiltonian, but it acts on the so-called two-side wave function, which is just the part of the wave function which contains all the degree of freedom for 2 sides. Okay, so what I mean by this is from this two-side wave function, which is a tensor, you can measure all the local expectation value of any local operator for a given two sites. And in particular, you can also construct the two sites reduced density matrix. Okay, so we had this like huge problem, and then we reduce it to a set of problems of optimizing two-site wave functions. Okay, and this is called, in general, this type of algorithms is called density matrix renormalization group. And it's precisely because you're essentially optimizing reduced density matrices at every step of the process. All right, and so the way this algorithm works is actually you kind of construct this effective Hamiltonian, and then you have a new, very easy Eigenstates problem to solve. And so if you are interested in having ground state, as in standard DMRG, you just solve the ground state recursively of all these effective Hamiltonians. And in our case, it's a bit more complicated. And essentially, what we are doing is solving Eigenstates, eigenvalue problems for highly excited states. So it's a bit more technical to understand how to do this properly, but essentially that's what we are doing. So we are just generalizing the ground state algorithm. Okay, and that's how you manage to have this huge eigenstates here. Okay, and this works only because there is not too much entanglement in our system. Okay, but so these kind of algorithms have obvious limits, right? And the first limit you can think of is that it works only on the MBL phase. So now if you want to study the full transition, we cannot use this MPF algorithm. And so it's nice to have a sense of how well our graph theory algorithm is working, and so to be able to match our results with theory. So we go back to smaller system sizes, and then we can do this process for the full phase transition. Okay, and so what we do precisely is we, for every eigenstates for this full phase transition, we measure the average number of clusters, right? And we divide it by system size. And we do this as a function of this order. And what is interesting is when we do this, we are able to recover scaling prediction from theory. And also we can recover results from other methods, right? But in a very cheap manner, because once again, once you have calculated the eigenstates, it's really take a fraction of a second to get the clustering. Okay, so this rescaling, which worked quite well with precisely like the correct critical exponents, comfort us in the idea that we are doing something physical when we do the clustering of the system. Okay, and just here I think it's interesting to do a small remark that our clustering algorithm works well when there are actually clusters in our system, right? So if you are fully into the thermal region, so let's say you are you are in this region where you have only one big ergodic cluster, we cannot really apply our cluster algorithm because there are no clusters to find. And what we do is that we look, so we can still do this decomposition, but when we find the best quality of the system, we can see if this quality is too low. And at this point, we say that we have obtained only one big cluster, right? Because the decompositions that we find are just with too low quality, right? And so this graph theory also gives us a criterion to distinguish between MBL and ergodic, and that's why we can explore the full phase transition. And we can also like distinguish between MBL and ergodic by looking at the entanglement, for example, and we would get exactly the same results. Okay, so now we have seen how to probe the static properties of MBL, but as I've said, we use only correlations which are accessible in experiments. So it would be interesting to see what we can do for experimentalists as well. And so this would be dynamics, because what they can do in experiments is prepare an initial state and then do a quench of this initial state, right? And now we would like to see if from our method we can identify the MBL phase and learn more about this MBL phase. Okay, so what we typically do is we start from a product state, which is easy to prepare in an experiment. Then we do the time evolution, and during the time evolution we can take some snapshots, right? So we can measure the correlations. So we have a different correlation matrix depending on time, and at every matrix, right, we can apply our algorithm and find the clusters, right? And so an example of one realization is just presenting on this slide. So at time equals 0, of course, there is no correlation, so there is nothing to see. But at the beginning, at time equal 10, you see that we identify 3 clusters which are very well defined. But now when you reach time equal 100, you see that, okay, first some of the clusters start to break up a bit because correlation spread. But also, very interestingly, there are very strong off-diagonal elements here, right? Meaning that our blocks interact with each other. Okay, and this is even identified at later times. But what you see, interestingly, is even at very long time, you still have quite good cluster structure. Okay, and so this kind of behavior is exactly echoing this logarithmic growth of entanglement. Right, so we can do this. So this was just one configuration to have an idea of what is going on, but we can just average over a different disorder realization, as we should do. And so we can measure, for example, the average length of the blocks as a function of time. And without surprise, we find that it slightly decreases as a function of time, but actually not so much, right? So you can still, on this configuration, have an idea of what was the initial block structure. Okay, so first we have a first marker of the MBL phase here. But I think most interestingly, we can see a decrease of the quality of our partition. Okay, so when we measure the quality, we do the average, we have this slow logarithmic decay of this quality factor. Okay, so this quality factor we have to take into account the system size dependence, that's what is rescaled, but otherwise we have this nice decay of the quality. Okay, and here also we are able to distinguish between the interacting case and the non-interacting case, because if we do the same thing for Anderson localization, I mean, first the blocks are not separated, right, during time evolution, and also the quality measure just decreases a bit at initial times and then just saturates. Okay, and this behavior is really reminiscent of what I've shown earlier. So let me just show this slide again. When you look at the entanglement growth as function of time for these systems, you have this kind of logarithmic growth of entanglement for MBL, but you have a saturation for the Anderson localized case, right? And that's exactly what we observe. So we observe this kind of saturation of entanglement in the non-interacting case, and then we have something which echoes this logarithmic growth of entanglement, and that you can directly measure in experiment, which would not be possible for this entanglement, right? It's very hard to do the full tomography of the states. Okay, and so this brings me to my conclusion. So we have seen that MBL is kind of very important because it's a primary example of a robust way to escape thermalization. In order to understand better the phase transition, we have used graph theory in combination with correlations, which are easy to obtain, and we have used also matrix product state to have large states. So we're able both to probe the static properties with the phase transition, but we are also able to do predictions which can be tested in experiments. And we have found an interpretation of a purely graph theoretical quantity, which is this modularity, this quality measure. And we have related this to the logarithmic growth of entanglement, which can be measured in experiments.
Okay, thank you, Kévin, for this excellent talk. Let us thank Kévin.
Thank you very much.
And we have time for questions. So, Dario?
Yeah, so I mean, I'm not sure. I probably you said, but I lost. I mean, I understand that in the MBL phase, you expect to have many, let's say, small clusters, because somehow is what characterizes the MBL phase, right? But I probably don't get the difference between, let's say, this, let me say, diagonal and off-diagonal clusters. I mean, qualitatively, why they are so different?
So it's not that they are so different, right? But this is exactly, so this, for example, green cluster, right, would be an example of this ergodic skeleton, right? Where you just have side 2 and side 4 correlated, but they are jumping over side 3, for example.
Ah, I see.
Right, so this would be a kind of small example of an ergodic skeleton. Right? And we could have, you know, like, we don't know a priori what we could have obtained, and it could have been like, you know, one big cluster which would span through the whole chain, right? In which case the picture here would have been completely different, where this, I don't know,
see.
green cluster would connect like sites very far apart. Okay,
so in principle, this, I mean, in a full, you expect that going far in the MBL region, this off-diagonal clusters will tend to disappear.
Right, but what we find, and also like people using like other techniques using exact analyzation, have found that even when you are close to the transition, it's still a minority, this delocalized.
Okay.
Right.
So they suddenly appear immediately crossing the transition, because that, I mean, in the ergodic regime, I would expect to find many of them, right?
Right, but in the ergodic regime, actually, there are no blocks anymore because there is just one blocks everywhere, right? So this confirms a bit. This confirms a bit this picture of thermalization avalanche, right? Where you have local blocks, and then this local blocks just, so the thermal blocks invade also like the insulating block. Right, but this could have been like a different thermalization avalanche where all these red blocks, right, would be in the rare thermal region, would be correlated with each other. And what we find with MPS is that this is not the case.
Okay.
Okay, we have a question from Munjip also.
Hi, thanks for the nice talk. So, I have a question. So if you use MPS to represent your state, then you're already kind of assuming area law entanglement, right? So it's kind of like you're assuming your hypothesis already, and you're restricting your answer. So how does that?
But the answer is that if we try to do this algorithm, let's say in the thermal phase, we see that it does not converge, right? And so there are things we can measure to say that, okay, this is not converging.
Okay, so can you elaborate more? What do you mean by it does not converge? So like it.
So right. So I mean, one obvious measure we can use is the variance of the state. So we have an eigenstate, right? And then we just measure the variance of the state. And we can see if this is below machine precision or not. And then if it's below machine precision, then we expect to have a good eigenstate, right? But also, like if you try to do this for, so for example, you do this in the MBL case, and you look at the energy as function of time, right? And the energy just kind of at some point converges, and all the observable converges. And this would never be the case if you would not have something which is area law.
Okay, so you're saying that your DMRG routine fails. That's what you're saying in the
right. So the DMRG fails when it's not applicable.
Okay, I see. So okay, thank you very much.
I mean, you can have some artifacts again, like let's say superposition of states, but you would be easily able to detect this using variance.
Maybe isn't there a chance that you still get the convergence, but actually true state is the thermal state, but since you're using DMRG, so it kind of miscapture the ambient state.
Right, so but since we have this kind of measures, like such as the variance is highly unlikely, right? We would see it failing. But what is possible, and that's what a bit the limits of our method is, since we have very small level spacing in our system, you can always imagining the algorithm like converging toward a superposition of states which are nearby in energy and which are combined in such a way that the entanglement decreased, right? So this is a possibility.
Okay, I see. Okay.
But okay, you don't expect this in MBL. So we don't expect this kind of thing in MBL, although we need to be careful always. So that's
okay. Thank you very much.
Yeah, of the algorithm.
Yeah, thank you very much.
For the question.
Can I add? Probably you don't expect that because since you are in a MBL phase, you expect that states that are very close in energy will be very different from each other, so they don't mix well together. I mean, is it possible?
Right. So that's exactly the expectation. Now it's not a guarantee. So like the states you obtain, they are qualitatively correct. We expect that most of them are eigenstates. But no, it's possible that among the 100 states you obtain, maybe 10 will be this kind of superposition, right? And this is particularly true if you explore very large systems, because then the level spacing become
very small. Yeah.
And then we cannot really control anymore, right? And actually, there are papers where they do benchmark on non-interacting system, right? This Anderson insulator, and then you can also there are also techniques to get the exact state, and define exactly this, that in the majority of cases that it's fine, but you can still occasionally find this kind of superposition. And that's true that it's a problem. That's true that it's a problem, and that's why it's very hard to have like very precise results today using MPS. But yeah, we just hope that the technology will improve. Because the barrier is not so like if we would want to do this for thermal phase, there is no chance that it will work because we cannot represent the state. No, we can represent the state, but we have not yet a completely safe way to obtain the eigenstate. Right?
Okay.
Mm-hmm.
We have also a question from Alexei.
Yeah, I have a simple question. So did you look at the quasi-periodic systems? So the example you gave here, you have two random fields. So do you expect any changes if you look at the quasi-periodic systems?
Right. No, but so we expect that what we have found for this like random potential would also work for the quasi-periodic potential. But
yeah, I mean, I'm sure your method still works there. I'm just curious.
Right, but that would be interesting to see. You know, like what would be like the relationship? Can you infer the block structure directly from the quasi-periodic potential? That would be interesting to see.
Yeah, I'm even curious. So you're sure that you would still find these clusters?
Right. So it's very likely, yes.
Okay.
So, but no, it's not clear whether we have qualitatively the same thing, right? So maybe there are plenty of other localized systems, right? There is, for example, something which is called Stark MBL, which is
yeah. That was my next question. I mean, basically, do you think there will be any difference between like, say true disorder, quasi-periodic disorder, or disorder-free?
Right. So probably there will be some kind of differences. No, it's very hard to to predict what will happen. But I mean, one case I think which would be very interesting is that this long-range interactions, because you can do this kind of MBL with longer range interaction. I know it would be interesting to see whether we have more delocalized cluster. I think that would be.
Yeah, that was something that I was going to ask. I mean,
yeah, that would be really the next step of doing this.
I see.
Right, because maybe then we could have like different quantum avalanche scenarios depending on what is the particular details of the system.
Somehow related to the thing of avalanches, I mean, I know of another debate about the existence of not of the mobility edge in the thermodynamic limit. I mean, even if we all agree that in the thermodynamic limit there exists MBL phase, somebody say, well, maybe the mobility edge is a finite size, and it is related to this avalanche scenario. So is your method in any way useful for this like, I don't know, I mean, can you, for example, go in the proxy? No, because your method only apply in the MBL side, so you cannot see any you cannot say anything, let's say, when you cross the edge, right?
Right. So I mean, so imagine we will have the perfect MPS method, right? Something we could do is try to go slowly towards a phase transition, and at some point we would see a failure of the method. And then we could say, oh, it's roughly there that there is a transition, right? And then we could see where it fails as a function of system size, and see, like, let's say if you increase the system size, then you have something more straight, right? Now, to be honest, like the technology is not so precise that we can really go close to the transition. It's very risky to do this. We can have this kind of superpositions, and right. So it's. I mean, we can try to do this, but I would not bet my life on the results. Right, but if the MPS improves, which is possible, then maybe one day we'll be able to.
I have a related question. Maybe if you can go to the next page with this finite size scaling. Maybe I misunderstood something, but it seems that you do see a nice transition, right, from this inset here. So the question is this your kind of estimate for the transition point, and do you see some sort of drifting? So in some previous works, there was this drift observed that with larger system size transition seem to be going. Do you also see this, or?
So yeah, so first, like the estimate is around like 3.7 for the phase transition, and this was taken also from another study. So we directly put like what we thought was the best scaling and what should be. So with this number of clusters, so there are other people who have other methods of having an estimate of this, and we took directly their parameters and it works perfectly. Right, and then I mean you see the collapse is not perfect, but so it's hard to say whether there is a drift. And to be honest, to really know this, we would need to go to much larger system sizes. I mean, but you can have like a reasonable physical picture from these small system sizes. But to resolve the debate of whether the transition shifts, I mean, we have to go to larger systems.
So why are you here considering 16? Before you were showing 50 in some cases. Have I missed something?
So the point is here we want. Yeah, right. So here the point is that we want the full phase transition, right? So maybe with MPS we can be at the right of this phase diagram. But no, we will never be not. So first in the middle we cannot go there, and then in the ergodic case it's impossible. Right? And
so this is not MPS.
Right. So this is ED results, right?
Okay.
Right. And, but this is very useful to have, like, at least to test whether we get something which is related to this theoretical approaches. Right, and it seems to be very related. So maybe our method is not the method you should use to establish a phase transition. Maybe it's simpler to look at the entanglement entropy and see the rescaling, right? You want to do ED results, but still it confirms that we are, like on the right spot. We are looking at something pretty different.
Okay, thank you.
What is the value of the exponent u here, and is it related to any theory?
Right. So here from memory, the u here would be around 2.5. Okay, and right. So first, it's quite close to some ARG pictures where they have like found some KT and so Costelli-Thouless behavior of the phase transition, but also it's compatible with what it's called the Harris bond, right? So because you have this order, you can have a bond of, so if you let's say put in like a particular scaling hypothesis and then you input the disorder, you can prove that your scaling exponents u should be greater than 2. Okay, and this is compatible with this bond, and that's kind of good news because there are some studies actually where they have looked at this transition and they did not find a u which was compatible with this bond. So there's further indication that we are also looking at the right.
U is somehow related to the exponent for the correlation length, isn't it? And I'm not sure what the correlation length is. Is it related to the cluster sizes?
Right. So that's an interpretation you can have of the cluster sizes. You can say that the cluster size is related to the correlation length. But actually,
have you studied the cluster sizes as function of W to check that?
Right. So that's exactly what we have here, right? So we have the.
Yeah, but that's indirect in a way.
Right.
You can measure the sizes of the clusters directly from your samples.
Right. So, but it would be something like 1/n, right? So either you look at this way, either you look at the length of the cluster, and you will have like the opposite graph.
Okay.
Right, and the rescaling works exactly the same. Right, and also maybe to say a bit more about this localization length. The localization length, the most rigorous way to define it, I think, is to look at this integral of motion, right? And you say that the localization length responds to this localization length of this conserved quantity, this tau z operator.
Thank you.
You're welcome.
Alexei has something further to ask or add.
Yes, actually, I'm wondering, I recall one more example where maybe you might be interested to look for clusters. Do you think your method can be also applied to the Fock space localization?
Right. Yeah. So yeah, in principle, we could do such things. But I think in this kind of Fock space localization, people already like use percolation numbers or such things like this. But I think they have already the tools to study this kind of phenomenon.
Yeah, well, then it might still be interesting to compare whether your method gives similar results or not.
Yeah, right. Yeah, and also, I mean, I would like to mention that here we have looked at out of equilibrium, but it's also interesting to look at this graph theory method. Maybe in equilibrium setting, maybe we can detect phase transitions. So, and actually, when we put the preprint, people roughly at the same time have used similar methods to look at phase transition of the ground state of 2D systems, for example. Right. So,
what kind of phase transition?
I think they were looking at supraconductivity, like U-boat model.
So they basically rely on the fact that for specific phases there should be some specific structure of the clusters.
Exactly right. So right. So I think what we show here is like it's worthy to understand the structure of the state to look at correlations coupled with graph theory, right? And this is more general just that for. So it's very convenient for MBL, but you could apply this to different settings.
Okay, thanks.
You're welcome.
Do we have any further questions or comments from the audience? It seems not. So in this case, let us thank Kévin again. And with this,